Welcome to this explainer. You know that feeling when a problem is just so massive, so incredibly complex that your brain literally just short circuits? Yeah, we've all been there. Today, we're going to completely upgrade how we tackle those impossible problems. We're drawing on some absolutely fascinating core concepts from computer science to give you a very real, very actionable problem-solving toolkit. Okay, so let's dive into this frustrating boss battle scenario. Just picture this, right? You're faced with a seemingly rigged game. It's that classic classroom setup where your teacher challenges you to a simple game of strategy and somehow, no way, they always come out on top. It feels like magic, or honestly, just kind of unfair. But guess what? It's actually just a matter of structured thinking.
Let's look at the exact rules of this game. On the table, you've got a line of colorful candies, and at the very end, a spicy red chili pepper. Here's the challenge. Each player takes turns, and on your turn, you can choose to take 1, 2, or 3 candies from the table. Obviously, you want the candy, but the ultimate goal is survival. Because if you get stuck taking the chili on your turn, boom, you lose. Try as you might, if you're just guessing or playing randomly, the teacher is going to maneuver you right into that chili pepper every single time.
But hey, don't panic. To beat the teacher, you really don't need luck. You just need methodology. We're going to use the Cambridge IGCSE Computer Science Problem-Solving Framework. Now, these are the exact tools programmers use to build super complex software, but they apply perfectly to winning this game and, honestly, solving massive real-world problems.
We're going to attack this logically in 4 steps. Step 1, break it down. Step 2, identify systems. Step 3, sequence the steps. And Step 4, follow the algorithm. Let's jump right into Step 1.
Think about trying to drag a massive, solid, totally unmoving block. That's exactly what a complex problem feels like when you try to solve the whole shebang all at once. It's exhausting. But if you realize that block is actually made of smaller, individual pieces, well, moving it piece by piece becomes entirely solvable.
So, the absolutely crucial point here is that this process is called decomposition. Decomposition literally means breaking a big problem down into smaller, way easier pieces. And why is this so vital? Well, big problems make us feel confused. We get overwhelmed, and our brains essentially just freeze up. Decomposition stops that overwhelm entirely. It lets your brain focus on just one small, easy-to-understand problem at a time. Suddenly, defeating the teacher isn't this huge, impossible task. It's just a series of small, manageable choices.
Let's see how this builds into our next concept, systems. When you break a problem down, you start to see it's not just a random pile of pieces, it's a system. So what is that? A system is a set of interacting or interdependent parts that form a complex whole. Think of our candy game. The players, the rules, the number of candies left, and that dreaded chili pepper. They all interact. A choice you make right now directly affects the state of the board for your opponent. It's a complete, living system.
And if we zoom in even further, we start looking for subsystems. A subsystem is a specific, self-contained unit living right inside that larger machine. So if the whole game of candies is the system, a subsystem might be isolating just the last 4 items on the table, the 3 candies and the chili, and figuring out the specific math just for that endgame scenario.
Now, you might be wondering, why do we even bother isolating these subsystems? Well, 3 reasons. First, isolation. This helps you find exactly where a problem is hiding. If your bicycle wheel is rubbing, logical decision-making tells you to check the brake subsystem, definitely not the bell. Second, specialization. It lets you focus on one job at a time without getting distracted by the rest of the machine. And third, connection. It helps you see exactly how pulling one lever, like a brake lever, directly affects the wheel. In our game, taking 2 candies is a lever that directly affects the teacher's next move.
Moving on, our third concept is sequencing. This is all about the order of operations. Think about it. If you do steps out of order, the results can be totally wrong, or it just might not work at all. It is a guaranteed glitch. Good sequencing is exactly like following instructions for a perfect Lego set. Each step absolutely depends on the one right before it. You can't put the roof on the Lego house before you've built the walls, right? In problem solving, you have to execute your perfectly decomposed steps in the exact right order. Okay, so we've broken the problem down, we understand the interacting systems, and we know we need a perfect sequence. Now it's time to put it all together into the ultimate tool to ensure victory.
That tool is the algorithm.
And listen, an algorithm isn't just some fancy tech buzzword. In computer science and logical problem solving, an algorithm is simply a rigid, foolproof set of precise rules or a sequence of steps designed to solve a problem. Often, programmers use flowcharts to map these out, really visualizing the exact path of logical decisions from start to finish. When you have a perfect algorithm mapped out, you don't have to guess anymore. You just execute the steps and success is mathematically guaranteed.
But you can't just write down any sloppy list of rules. For your logic to work perfectly, your algorithm actually needs these 5 specific glitch-free traits. First up, input. It needs starting data to work with, like counting exactly how many candies are on the table. Second, output. It must always produce a result, which is your calculated move. Third, definiteness. Every single step must be perfectly clear and unambiguous, absolutely no guessing allowed. Fourth, finiteness. It has to end. It can't just run in an infinite loop forever. And fifth, effectiveness. The steps have to be simple enough to actually carry out. If your algorithm requires you to do quantum calculus in your head on the fly, well, it's not effective. Keep it simple, clear, and definitive.
So you now possess the entire problem-solving toolkit. You know exactly how to decompose that massive block into manageable pieces, identify the systems, sequence your actions, and formulate an absolutely airtight algorithm. So, looking back at that table of candies, which piece of the puzzle are you going to decompose first to map out your winning flowchart and finally leave your teacher with the chili? The game is entirely in your hands.